All right. So slides from last time. If you don't mind, could we all of us mute our microphone, and then if you need to ask questions, just enable them again. Thank you. Okay, so hopefully we're ready to begin. So this is where we were last time, talking about the I think the major physical process inside a solar cell operation. I made some amendments here regarding the description. Mainly, I really want you to be able to distinguish between actually the typical energy efficiency, which is something actually we mark here, right? This is the energy efficiency definition we typically use. But if you consider the major physical process, then it's actually more helpful for us actually to look at things from the other efficiency point of view. That is the so-called quantum efficiency. Okay, so with the quantum efficiency, we basically look at actually the whole process inside the solar cell, from the input, the incident solar spectrum. Okay, and then it goes through an absorption process, which is actually going to be the first process we will cover later. And then after the absorption, what happens? We have to excite actually the charges. Specifically, we have to create the electron and hole pairs, from the excitation, okay, electron and hole pairs. And then afterwards, we still have to find a way to separate, to dissociate the electron and hole pairs so that they can be free charge carriers, because it's only from free charge carriers we can generate current. Okay, but first of all, in order to have the separation event, this electron and hole pair, they have to actually diffuse or drift actually to the p-n junction interface. Okay, remember we mentioned that for a certain p-n junction, only at the space charge region, in this location, do we have actually the electric field necessary for the separation. Okay, so first of all, they have to find their way actually to be inside the space charge region. Of course, there is the special case if the excitation happens directly inside the space charge region. Then in this case, you practically do not need to do any kind of drift or diffusion. In this case, the drift or diffusion efficiency, it will be 100%. Okay, but if the excitation, if the absorption happens outside of the space charge region, in this case, you may face some losses from the drift or the diffusion efficiency. Okay, so that is basically the third process we talk about here. And if they successfully made it into the space charge region, then there is also the separation efficiency, because it's not going to be 100% efficient to separate the electron and hole pairs, because naturally they are attracted towards each other. Okay, but if we're able to separate them, then at this time they become free charge carriers. So typically holes actually will tend to move towards the p-type side, while electrons will try to move towards the n-type side. Okay, because with the electric field, automatically they will be pushed actually towards opposite directions. Okay, because as we said, normally the electric field inside the space charge region, it is from the n-type to the p-type side. So electrons will be attracted to the positive, while holes will be attracted to the negative side. Okay, and then at the very end of the p-type n-type region, we should have the electrodes. Okay, we should have the electrodes. On the p-type side, this is usually denoted as the positive terminal. On the n-type side, this is typically as denoted as the negative terminal. So for these electrodes, they need to be able to collect these charges successfully. Again, there is another collection efficiency, because you may face some losses along the way. okay, along the way. So in the end, if you're able to collect, the charges successfully, we consider this as a successful generation of electricity from the solar cell. Okay, so basically all of these efficiencies, they describe actually the overall quantum efficiency from the solar cell. So in the end, obviously, the total efficiency, the quantum efficiency, it should always be between 0 and 1, or it should be between 0 and 100%. Okay, because all the efficiency that is involved, in the multiplication, it is always a number between 0 and 1. So if you multiply, the overall efficiency, it should be actually smaller than any of the efficiency that is involved. Okay, so what does it mean, the quantum efficiency? Quantum efficiency basically describes the probability for you to convert one photon, okay, into a certain, average probability of charge carriers. Okay, of course, if you have 100% quantum efficiency, it means that ideally speaking, from the physical perspective, you can convert actually one photon into one charge carrier, into one electron plus one hole. Okay, but if you have the losses, let's say you have a 50% quantum efficiency, it means that for one photon on average, you can only convert that into 0.5 carriers. So you generate half of the current compared to the ideal maximum case. Okay, this is actually very different from the energy efficiency. I just want to emphasize again, but there is a connection between the two. If you know the energy from the photon here, if we say that we give the input of one photon, obviously, if we know the energy of this photon, we have the input energy. Okay, so we have the input, if we have this information. And then for the charge carrier, specifically one charge carrier, you can calculate how much is that in terms of the current or current density, because we mentioned the current density definition from last time. So actually you'll be able to know how much current or current density we generate actually from one charge carrier. So the only missing information is that for energy or for power, we need to know actually how much potential we are creating from here. Okay, so if somehow you also have the potential from the solar cell, then in this case you can calculate the power or you can calculate the energy, because we're just talking about one photon case. Okay, so in this case, if you know the potential difference, if you know the photon energy, it is possible for you to convert actually the quantum efficiency into energy efficiency. Okay, you just need to add a couple of missing information. So you can see that there is actually direct correlation between the two efficiencies here, but physically they have different definitions. Okay, so this is actually one thing I would like to emphasize based on our lecture last time, and you can see that we added a couple of sentences here. Hopefully, this will make it more clear to you. Okay, so is it okay for this definition? All right. So, okay. Yeah. Let me know. Feel free to let me know if you need me to stop or or just to repeat a couple of things. But now let us begin on the diagram here. You can see that from the previous diagram, the first interaction that we should look into in the solar cell is the light absorption. Okay. So let us look at the light absorption process. Okay. Let's focus on the optical process first. So as we know, in order to generate electricity, solar cell has to absorb, incoming light. Otherwise, it's impossible for you to generate electricity. So in order to absorb actually, in order to absorb incoming photons, obviously there is a certain prerequisite. Okay, there is a certain prerequisite. And then, if we talk about a general material, okay, a general material, if there is incident light, incident irradiance on this material, what are the possible phenomena we can expect? Okay, what are the possible outcomes, from the incidents? In general, there are only three possibilities. Okay, there are only three possibilities with the incident photon on a certain chunk of the material. So first of all, there is the reflection. Okay, a certain portion or a certain percentage of the incoming irradiance, it will be reflected. So this is what we call the reflection. okay, reflection. We use the percentage here to indicate that this is a percentage term, okay, this is a percentage term. And then a certain part of the light actually would disappear inside the material, okay? Of course, this is provided that this material can absorb the incoming light, because we talk about, actually when we talk about the semiconductors, we mentioned that in order for semiconductor to absorb the incoming light, there has to be one condition, there has to be one prerequisite. So do you guys remember what is the prerequisite in order for us to absorb the incoming light? Does anyone of you remember that what is the condition, for a certain material to absorb a certain photon?
It should have energy above the band gap energy.
Very good, yeah, very good, Lifty. This is actually the band gap prerequisite. Okay, so in order for light to be able to absorb inside the solar cell, remember one of the prerequisites, if you allow me to go to the next slide, is that the photon energy must be larger or equal than the material band gap. This is actually the absolute prerequisite. Otherwise, we may see there is a zero absorption inside the material. Okay, so this is actually quite important for us to keep in mind. But however, if that's the case, if we can actually absorb the incoming light, then of course a certain percentage of light actually will disappear inside the material, and this part is known as the absorption. Okay, again, we are using actually the percentage here to indicate that the absorption is a percentage term. Okay, it's important for us actually later we will talk about several words very similar to the word absorption, but each of them, they may have a different meaning. But for the moment, whenever you see the word absorption mentioned, okay, automatically you should reflect that this is actually the percentage term, percentage 8, that's the absorption. Okay, and finally, if the material is thin enough, meaning that not all of the photons, not all of the irradiance can be absorbed inside the thickness. In this case, a part of the irradiance may come out from the backside of the material. Okay, and this is what we call the transmission. Okay, transmission or percentage transmission. Sometimes we use another word for this, but essentially most of the time they carry the same meaning. Sometimes we say that it's not transmission, but it's actually transmittance. Okay, transmittance. Actually, these two words in our lectures context, they have the same meaning. Okay, they have the same meaning. So just remember that this is also a percentage term. So if all of them are percentage, automatically we have actually this equation that all the percentage when added together, they should automatically equal 100%. Okay, because we're basing the percentage on the irradiance, and the total irradiance should always be the same. You just have these 3 possible scenarios for the incident irradiance, for the incident photon. Okay, so typically we denote the incident irradiance as E0 or E0. So this is the initial irradiance. Okay, this is the initial irradiance. And then if we have the percentage for reflection, we just need to multiply the incident irradiance by the percentage, the reflection, the percentage reflection by the initial irradiance. And this will give us the reflected irradiance, okay, reflected irradiance. So this will be percentage R, okay, times E0. And then the part that is being absorbed, very simple. We just use the E0 multiplied by percentage absorption. Okay, and finally, the last one should be E0 times percentage transmission. Okay, percentage transmission. So we have actually all the terms we have, that is shown here in this slide. Okay, so we describe actually the 3 possible phenomena: reflection, transmission, and absorption. Obviously, we are most interested in the absorption phenomenon. Okay, so what is the general behavior for the absorption? So we define the percentage, but if we want to know how much we actually got absorbed inside the material, what is the typical feature? Actually, it follows a very simple relation. Actually, inside the material. So when a certain irradiance Okay, so the I here indicates intensity, and for light signal, this is equivalent actually to the irradiance. Okay, this is irradiance. So the irradiance, when it enters a certain medium, when it enters a certain material, okay, it always follows a single exponential decay inside the material. Okay, so the deeper the irradiance is entering or penetrating, basically the more decay, the more exponential decay we will be seeing. And it is going to be a single exponential decay. Okay, so with this is actually based on the so-called Beer-Lambert's law. Okay, Beer-Lambert's law. So basically, it's saying that the irradiance, on the front surface of the material, if we call this irradiance E1, okay, this is not exactly the E0 that we mentioned, because remember, actually, if we have an incident irradiance E0, actually part of the irradiance will be reflected. Okay, so specifically E1 here should equal the initial incident irradiance minus the reflected irradiance. Okay, minus reflected irradiance, because we just need to know the irradiance on the very surface of the material. And then from there, if we have the irradiance at the zero depth, at the zero thickness, we just need to multiply by a exponential decay that is related to the thickness. Okay, so x is the depth of the material or the thickness of the material. But then there is a coefficient. This coefficient is the so-called absorption coefficient, which is here. Okay, it's a decay, so that's why we have a negative sign here. Okay, we have a negative sign here. So the alpha is the absorption coefficient. Okay, alpha is the absorption coefficient because we're using alpha times the depth. So the unit for alpha is actually centimeter inverse. Okay, it's actually centimeter minus 1. Okay, so that they will cancel each other, and then you can simply, this will become a simply coefficient to multiply the incident the irradiance at the surface. Okay, so that we have with this equation we can calculate the irradiance at any certain depth of the material. We can do that. Okay, so you always follow this exponential decay. And as we said, E1 is actually the difference between the initial irradiance minus the reflected irradiance. So you can also write the E1 as this way. Okay, you can also write E1 as this way. So that is the absorption coefficient. And I just want to point out that this is not exactly the same as our absorption, percentage absorption we just mentioned. Okay, so you can try to think about the relationship, between the absorption coefficient alpha and the percentage term, percentage absorption, percentage alpha, percentage A. Okay, what is the relationship between that? Obviously, you have to take the thickness into consideration. Okay, you have to take the thickness into consideration. How much percentage you can absorb inside this material, it depends on actually the thickness of the material. And obviously, the larger the thickness, the more absorption that can take place. Okay, that can take place. So in the end, this will increase actually your percentage A. Okay, but at the same time, the absorption coefficient, it should be a constant for a specific material. For a specific material, the absorption coefficient should always be the same, because basically it says that the per depth, how much exponential decay we are expecting. Okay, so this is actually the difference between the two terms. Okay, between the two terms. Because we're talking about exponential decay, there is another term that we typically use, to reflect how capable the material is in absorbing light. Okay, this term is the so-called penetration depth. Okay, penetration depth XE. Okay, XE. What does it mean? For that you need to look at this plot. Probably it's better to rotate this by 90 degrees. Whenever we are dealing with the exponential decay, okay, if we want the certain thickness to reflect actually the capability of the material to absorb, we would like this thickness to correspond to the intensity decay to exactly 1/E. Okay, to exactly 1/E of the original irradiance. So the original irradiance is here, is E1, and we would like to find the thickness that corresponds to a ratio of 1 over E. Okay, you can try to calculate how much is 1 over E. You know, it's actually roughly around 30%. Okay, around 30%. So this means that at this thickness, most of the incoming irradiance, it has been absorbed. Okay, it has been absorbed. So this is like a signature thickness for this material. It means that, for instance, if we calculate this penetration depth, let's say to be 100 micron. Okay, just an example. If we have 100 micron for this for this material, for the penetration depths for these wavelengths, then it means that this provides us with the guideline of the thickness. So when we design our solar cell thickness should be similar, or should be in the order of the penetration depths of 100 micrometer. Okay, so if our solar cell is 150 or it's 200 micrometer, most likely we will be fine, you know, because we will be able to capture most of the irradiance. However, if our solar cell thickness, you know, it is only 10 micrometer, it's one order lower compared to the penetration depths, obviously we're going to lose a lot of irradiance. Because they will come out from the back. They will become transmission instead of absorption. Okay, so this means that based on the guideline, the thickness is actually too small. Okay, so that is the importance actually for this penetration depth parameter. So if based on the definition, you know, so we can write further like this, you know, at the penetration depths, you know, based on our definition. The irradiance here, you know, which is E1 times exponential minus the absorption coefficient times the penetration depths at this time. Okay, this should equal actually E1 times exponential minus 1, because we're talking about the 1 over E. Okay, we're talking about the 1 over E here. Okay, 1 over E. So this means that this term will have to equal minus 1. Okay, will have to equal minus 1. So you can just simply shift actually the alpha to the other side, and this is our calculation. We can simply do the inverse of alpha here to find actually the penetration depths. Okay, it's actually very simple to find, and then from there we have a very quick estimation about actually the thickness that we need in order to absorb most of the incoming irradiance. Okay, so this is actually the Beer-Lambert's law. Okay, Beer-Lambert's law. This is based on this equation that we describe actually all of this phenomenon, the absorption phenomenon here. Let me go to the next slide. Okay. Next one. Okay, so we describe actually the absorption coefficient. Okay, it's actually very interesting for us to plot the absorption coefficient as a function of photon energy. Okay, as a function of photon energy, because you have to keep in mind that this absorption coefficient, the absorption behavior for a certain material, it will be different for different photons. It will be different for different wavelengths. Okay, because we just said that for instance, for a certain material, if the photon energy it is below the band gap, then obviously we know that at this time the absorption coefficient for these wavelengths, it should be 0. It can never absorb anything. Okay, so which is why actually it is actually important for us to look at the absorption behavior over wavelengths or over photon energy, because we know that the photon energy is related to the wavelengths. Okay, the photon energy should equal Planck constant times the speed of light divided by lambda. So it's actually the inverse of the wavelengths. Okay. At the same time, for a certain absorption coefficient here, we can always find the corresponding penetration depths, because the penetration depths is actually xp here. Okay, equals 1 over absorption coefficient. So actually, the two scale that you see here, they will correspond to each other. Okay, they will correspond to each other. So what can we see from this graph? Okay, there are so many semiconductors here. There are so many materials here. Let's pick the most familiar one. Okay, let's pick the most familiar one. That is the crystalline silicon. Okay, the crystalline silicon. So you can see that on the very left side of the plot, actually there is no absorption behavior here. Okay, we're plotting in log scale, but essentially to the left side of the plot, the absorption coefficient for silicon here, it should be 0 because of what? Because of the band gap we just mentioned. Okay, if you look at this point, if you focus on this point specifically, this is actually the band gap for silicon, which equals 1.12 electron volt. Okay, it means that for the incoming photon, if the photon energy is less than this value, then essentially you have a 0 absorption. Okay, you should have a 0 absorption. In this case, the penetration depth actually will be approaching actually infinity. Okay, it's going to approach infinity. It means that no matter how thick the material is, you can never absorb this part of the photon. Okay, and then you can also notice an interesting phenomenon. The absorption coefficient is actually increasing as we increase the photon energy. Okay, as we increase the photon energy. Why are we seeing this behavior? Why is this behavior reasonable? Well, think about the band gap model. Okay, think about the band gap model. We have a conduction band, we have a valence band. So the band gap is a fixed value for silicon. Okay, the band gap is a fixed value for silicon. So if you want to excite the electron from valence band to conduction band, and if the photon energy precisely equals the band gap, then in this case, yes, it's possible for you to excite to have absorption. But at the same time, because you have a very small margin here, you need exactly this amount of photon energy to make the excitation possible. Then actually you have a very little margin for error. Okay, so any kind of additional losses, any kind of a deviation, this will make actually the absorption impossible. Okay, but if the incoming photon actually has a very large photon energy, in this case you can allow more error. It's actually easier for you to make the absorption possible. Even if you have some losses, you have some additional losses, or you need the other kinds of assistance for the electron excitation. You're still within the capability to do that. Okay, so one thing we can notice for all the material is that if you have a higher and higher photon energy, it becomes easier for this material to absorb. Okay, because it's more relaxed in terms of the requirement for the absorption here. Okay, so you can see this behavior in practically any material that we are showing here, any semiconductor that we are showing here. It's always an increasing trend with the absorption coefficient. So inversely, for the penetration depth is actually decreasing. Okay, because the higher the curve, you can see that actually the smaller the penetration depth. It means that you need a thinner and thinner material to be able to capture most of the incoming irradiance. Okay, so that is actually the interesting thing here. And by the way, we also plot actually the wavelengths actually on the top axis. Okay, so it is inverted to the photon energy scale. Okay, and they correspond to each other precisely. Okay, they correspond to each other precisely. So we notice here, for instance, the crystalline silicon. It shows actually good absorption behavior, but at the same time, this seems to not the best material for the absorption behavior. Okay, can you find actually a material that is more capable compared to silicon here? Do we have other material that is more a better absorber?
Copper, indium, selenium at the top left.
Yeah, that's a very good observation. Okay, we have, for instance, this material, strictly speaking, it is better compared to silicon in every way. Okay, it starts the absorption earlier, meaning that it can capture more wavelengths, more photon energy. At the same time, in any case, the absorption coefficient is always larger compared to silicon. Okay, we have also actually another sulfate here. that beyond a certain photon energy, the absorption is more efficient compared to silicon. Okay, so it's actually quite interesting to see that actually a different material shows a very different absorption behavior, not just based on the band gap value, but later we will show you that actually there is another kind of factor or reason for the material to show, a lower or higher absorption behavior, because the band gap only determines the starting point. Okay, the band gap value only determines the starting point, but the slope of this curve, whether it shows a very fast increase or very slow increase, it depends on actually the semiconductor structure, which we will mention later. Okay, we'll mention later. But it's quite interesting to observe this phenomenon here. All right.
Hello.
Yes, you have a question? Is there any questions here? Okay. All right. Okay. So with that said, now if we have a material with a certain thickness, okay, we call this thickness that is the small letter lowercase d here. In this case, actually, with the new knowledge we have with the absorption coefficient, because typically absorption coefficient you can find this a constant for any given material. Okay. In this case, actually, we can try to correlate. Remember one of the questions we had before is that what is the relationship between absorption percentage versus the absorption coefficient? Now, actually, we can actually try to correlate these two terms. Okay. So for that, we would like to know at the bottom of the material how much irradiance is remaining. Okay. So basically, we want to know how much is E2 here. And E2 obviously is the irradiance at exactly the thickness of the material thickness. Okay, at the small lowercase d here. And how much is that? We just have to follow the absorption coefficient or the Beer-Lambert's law. Okay, which means that this equals E1 times the exponential decay, and here x equals the material thickness. Okay. So how much is the irradiance being absorbed? So we have E1, we have E2, and obviously the difference is actually the absorbed irradiance. Okay, that is the E absorbed. So E absorbed here equals the difference between E1 and E2, and we can actually find the full expression here. Okay, we can find the full expression here. So how do we define the absorption percentage? When we define the absorption percentage, and by the way, we have sometimes you will see another term that is basically the absorption percentage. Okay, that is called the absorption efficiency, which is by the way the first efficiency we define when we talk about the overall process for the solar cell. Remember that we said that for the total efficiency, it has to equal absorption efficiency times the excitation efficiency times etc. etc. Okay, so actually the first term, the absorption efficiency, it is directly our percentage A, because it means that what is the percentage that can be absorbed by the material. Okay, so the definition, if you want the detailed definition, it should be the number of absorbed photons over the number of incident photons. Okay, so that will give you the percentage. So for the same wavelengths, for the same photons, the number should be proportional to the irradiance. Okay, which is why we can correlate the ratio into something like this. So it should equal the irradiance absorbed over the initial irradiance, the incident irradiance. Remember that this one should be E0. It should not be E1, because E1 is not the incident irradiance. Okay, it's not the incident irradiance here. So if we substitute everything into the equation here, knowing that E1 is related to E0 by the reflection. Okay, so we can write actually like this: that the percentage A should equal 1 minus reflection. Okay, because 1 minus reflection is the part that is entering the material, and then multiply by this term, that is 1 minus exponential minus negative alpha times the thickness. Okay, and that is the correlation between the two terms. Okay, that is the correlation between the percentage A and the absorption coefficient. Okay, so with the equations here, it is possible for us, just by our design to estimate how much light will be absorbed by our solar cell. Okay, you just need to have the information about the absorption coefficient, and typically this is easy for you to find. If we are designing for a silicon solar cell, depending on whether it's a monocrystalline or multicrystalline, you can find the absorption coefficient. It's usually a constant for a given wavelength. Okay, and then if you have your solar cell thickness, you can combine the thickness, and then you can predict how much light will be absorbed. So it should be pretty easy for you. Okay, it should be pretty easy for us to do, and that's why I think that this part is actually quite useful for you. If you want to design a efficient solar cell. For efficient solar cell, obviously, we want the absorption to be as large as possible, okay, so that you can increase this efficiency as much as possible, okay. But here's the question: should we design our solar cell with the thickness so that our absorption efficiency is approaching 100%? So should we always go for maximum thickness so that our solar cell is very, very efficient in absorption? What can be the possible risk here?
Doctor, maybe we are going to affect the other components, which is like diffusion and recombination and others.
Yes, very good. That's a very good point here. Excellent answer. So actually, for that, you have to basically reflect to the previous, the process chart, the flow chart, basically. Remember that the absorption is only the first step. Okay, but afterwards we have so many procedures or process or efficiencies that is also dependent on the thickness. Okay, that is also dependent on the thickness. For one thing, we mentioned the drift and the diffusion for the electron and hole pair. Okay, so once you have an electron and the hole pair, okay, remember that they have to diffuse actually to the p-n junction interface. Okay, to the space charge region. So if you have a very large thickness for the material, the problem is that it has to diffuse a very long distance to be able to reach the space charge region. But then the longer you travel, the more likely these electron and hole pair, it will be lost on the way. Okay, so if you have the maximum thickness, yes, you can have a very efficient absorption, but the chance is that you are going to have a very poor diffusion efficiency. And after the separation, if you separate, the charges, holes actually will go this way, electrons will go this way. But if you have a very large thickness, the problem is that the longer they travel, the less the efficiency for you to collect them. Okay, so the collection efficiency will also jump. Okay, collection efficiency will also jump because you are sending them actually over long distance, and it's very easy for them to get recombined along this way. Okay, so what I want to emphasize here is that the solar cell, it is actually a optical and / electrical device. Okay, and when you make the design, you have to always balance between the optical performance as well as the electrical performance. With the absorption, actually, we can design a 100% efficient optical performance device, but at the same time, the electrical performance most likely will be very low, will be very poor. Okay, so in the end, it's not about maximizing a certain portion for optical or for electrical. In the end, it's more about balancing to find the optimum point, to find the sweet spot where you can actually, from there, you can get the maximum or the total efficiency, the total quantum efficiency from here. Okay, which is why we emphasize on this equation. It's not a single process that is going to be critical. It's actually the multiple combination from this process that is going to be very important for the solar cell performance. Okay, so that is something I just want to emphasize here. I'd like to spend a little bit of time here just to remind you about this consideration in your design. Okay, so moving on, we have some calculation examples. Okay, they should be relatively easy for you at this point. So first of all is to calculate the penetration depth okay, for crystallized silicon at this wavelength, 600 nanometer. This is in the yellow orange-ish color, spectrum. Knowing that the absorption coefficient for crystallized silicon at this wavelength is actually 4,000 centimeter minus 1, okay, 4,000 per centimeter. So in this case, what do we do to calculate the penetration depth? Very simple. It should be just the inverse of the absorption coefficient. Okay, so 1 over 4,000 per centimeter. Remember that this is in centimeter, but for penetration depths, typically we prefer to use the micrometer unit. Okay, so this equals only 2.5 micrometer. So it is only 2.5 micrometer. It means that for silicon at the 600 nanometer at this wavelength, the absorption is actually very, very efficient. Okay, because in theory, we just need the 2 micrometer or 2.5 micrometer, and then we can capture around 60 or 70% of the incoming irradiance. Okay. Did we mention the average thickness for crystallized silicon solar cell last time? Do you guys remember what is the average thickness for a silicon solar cell typically?
200 or maybe 150 micrometer.
Exactly. I think we mentioned last time, I think nowadays you are able to make a crystalline silicon solar cell with about hundreds of micrometer. Okay, I think we mentioned 200 micrometer, and it was 400 micrometer before for the wafer. Okay, but look at how small the absorption, the penetration depths here. For 600 nanometer, this is actually much smaller than actually the typical silicon solar cell. Okay, it is because at this wavelength, silicon has a very good absorption behavior. But why are we making the solar cell to be 200 micrometer? Because in the solar spectrum, it's not just a 600 nanometer. We have many more different wavelengths that we need to be able to cover, to capture or to maximize the solar cell absorption, the solar spectrum performance. Okay, so what you can see here is that actually, 2.5 micrometer, the calculation result here shows us that, if you want to capture 600 nanometer line, if you want to focus just on this wavelength, then around the order of 2 micrometer or 1 micrometer, this is enough for you to capture most of the photons here. Okay. However, knowing that, for when we design the solar cell, what we have in mind is the whole solar spectrum. We want to maximize our input from there. In that case, actually the 100 micrometer range is actually more reasonable for us actually to capture the whole solar spectrum. Okay, so should be a simple example to begin with. We have a follow-up example. Okay,
Doctor,
so
just a question.
Yes, go ahead. Go ahead.
Should we target the blue spectrum region because it has the highest intensity, or should we take the average over the whole spectrum for the thickness?
To answer this question, actually, if you remember the solar spectrum, okay, I'm plotting this from memory. If you have the spectrum irradiance versus the wavelength, actually the solar spectrum, typically shows a peak. Okay, and where is this peak? Actually, this peak typically is not in the blue. This is actually a sort of in the, I think it's around the 600 nanometer range or 500 nanometer range. Okay, so this is actually in the orange, in the red range for the spectrum. Okay, well, for the blue portion, typically is here. This is typically the blue portion. Blue portion per photon, we know that they have a very high photon energy. Okay, and yes, they consist of a significant portion of the solar spectrum. But these regions, they are not actually where you find the maximum irradiance in the solar spectrum. Okay, so that is one of the reasons that we choose the silicon in solar cells, because the band gap of silicon is actually is actually covering the peak of the solar spectrum. At the same time, it shows a very good absorption behavior around this part. So at least for the peak, we are able to capture actually the photons here very efficiently. Okay, but typically the blue part is actually hard to consider, because even if you find actually a material, a semiconductor that captures actually the blue part, okay, But remember, we mentioned another phenomenon from the blue portion in the solar PV lecture. That is going to be actually the thermalization losses. Okay, so even if you absorb the blue portion here, yes, the absorption efficiency, the percentage A is going to be very good here. But then, depending on the band gap, most of the time, in terms of the energy efficiency, you are going to lose some of the photon energy here actually from the absorption. Okay, so if you go from the quantum efficiency to the energy efficiency, remember we said that you have to consider also the potential from the solar cell. But then if you lose energy from this from the blue portion, the problem is that you are going to suffer a little bit loss in the potential. Okay, in the potential. So in the end, the blue portion, yes, they have a significant solar energy there, but at the same time, it's difficult to utilize them efficiently. Okay, even if you want to, but the thermalization losses, this will give you some headache, because if you focus too much on the blue, the performance in the yellow, in the red, actually they will drop, and then the performance specifically in the near infrared, they will also drop very significantly. Okay, because remember, most of the time your solar cell has one single band gap. Okay, you cannot actually cover all the spectrum positions. Okay.
Yeah, that's clear.
Is it clear? Okay, good. Yeah. All right. So let's look at the follow example. Now let's focus on infrared light. Actually, let's focus exactly on around this one. Okay. So for silicon, infrared light actually shows a very poor absorption coefficient. Okay. It's actually only 50 per centimeter. Okay, 50 per centimeter. So if we assume a 0% reflection, okay, it's very ideal. We know that silicon usually reflects a lot, but for the moment, let's assume that this silicon has no reflection. Okay, so we would like you to make an estimation. Try to see what is the minimum thickness that we need to have in silicon, so that we have over 99% of absorption. Okay, so if we want to absorb over 99% of the infrared or near infrared light, okay, what is the minimum thickness that we need? Okay, so first of all, if we assume zero reflection, and from the previous equation, the 1 minus r, basically this equals 1. Okay, so basically E1 equals the incident irradiance E0. So for the absorption percentage, okay, that equals actually the from the previous equation we have this one, but remember that 1 minus r is basically eliminated. Okay, so from here, actually, we write directly that absorption percentage equals 1 minus exponential negative alpha times the depth of the material, which is x. Okay, so we just need to find how much is the x here if the absorption percentage should be larger or equal than 99%. Okay, so we have here the exponential term should be less or equal than which is only 1%. Okay, which is only 1%. And if we solve this exponential equation, you can see how much is the thickness. Actually, the thickness is over 900 micrometer. Okay, it's over 900 micrometer. This is much larger than the 200 micrometer we find in the average silicon solar cell. Okay, and that is exactly what basically what I was referring to here. It's difficult for you to try to account for all the possible regions in the solar spectrum. Solar spectrum is very wide. If you focus on one region only, the other region, the performance actually it will suffer. Okay, so for the infrared light, if we want to absorb most of the infrared, actually you can see that we have to build a very, very thick solar cell. But going back to what we mentioned before, if you build a 900 micrometer thick solar cell, your electrical performance it's going to be very poor. Okay, you are going to suffer a lot of recombination losses. You are going to suffer a lot of diffusion losses. So, which is the reason why even though potentially we can absorb the infrared light, but in theory we're never going to build a very thick solar cell. Okay, so this is actually the reason for this. Okay, this is actually the reason for this. And a follow-up question, just for you to maybe to try some calculation or just to think about it. Okay, so here we assume an ideal case where we have a 0% reflection. But what about, where we know that the silicon typically shows an average refraction of 30%. So what about if you repeat the calculation, but this time you add the 30% refraction back into the question? Okay, how would this affect the calculation results? What should be the minimum thickness we're targeting here? Okay, so you can probably imagine that if the initial reflection is already 30%, the maximum absorption is going to be always less or equal than 70%. Okay, so actually this question is no longer valid. We can never do 99%. Actually, the maximum we can do is 70%. And from there, you can try to see, for instance, if we have only 1% losses, if we want to maintain, let's say, maybe 69%, absorption, what should be actually the thickness? What should be the minimum thickness? Okay, it's going to be much larger than this. That would be my estimation. Okay, that would be my estimation. You can give it a try to and let me know if it's the case or not. Okay, so this is actually the second example we have here. Right, so the last point we would like to mention for the optical behavior is that typically if you read papers, sometimes they will mention another parameter that is very similar to the absorption, to the percentage absorption that we use here. But there is a certain difference, okay? So this term is called absorbance, okay? This is called absorbance. So percentage absorption is coming from actually okay, the word absorption, but this is absorbance. So for absorbance, typically we use just the capital letter A instead of the percentage. Okay, so how do we define absorbance? You need this information because in sometimes in literature, sometimes in the simulation, they use absorbance instead of absorption. Okay, so what is the absorbance? How do we define absorbance? Actually, absorbance is defined in even I think in a more simple way. Okay, it only look at the input and the output actually for the material. So assuming that this is your semiconductor, and we focus just on the input and the output. Okay, so basically for the same wavelength, the intensity is proportional to the irradiance. Okay, and then if you remember, actually, after the material, actually we typically use the irradiance E2 to refer to actually the transmitted irradiance. Okay, so with the definition, basically it says that the absorbance is a log ratio parameter. It equals log 10, and then I0 over I. So if we follow our definition here, this is essentially E0 over E2. Okay, E0 over E2. And E0 over E2 is basically the inverse of transmission, because we know that the E2 equals the incident irradiance times the percentage transmission. Okay, times the percentage transmission. So basically we have a very simple relationship for absorbance. It is only related to transmission. Okay, it is only related to transmission, and because the transmission is a percentage term, what we can do here is that we can convert this, multiply by 100 on both sides. Okay, on actually on the top and on the bottom. So this will be 100 over 100 times percentage t. Okay, percentage t, and then since we're doing log 10, so if we take the top part, log 10 100 equals 2. Okay, and then the bottom part will become log 10, and then it's going to be percentage t times 100. Okay, so this means that if you have let's say a 15% transmission, okay, so you can write actually absorbance as 2 minus log 10, okay, and then 15% times 100. So this will become 15. Okay, this will become 15 only. So you can see actually one thing from here is that the absorbance, right? Absorbance issue actually it is actually starting from around 2. Okay, because actually for the part afterwards, log if it's a log 10, log 15, log 30, typically this part it should be positive. Okay, so typically your absorbance should always be less or equal than 2, unless your transmission is really small. Okay, for instance, your transmission is less than 1%. In this case, yes, this part it can be negative. In that case, you can have a very large absorbance, but that is actually quite unusual for you to find. Okay, so with that, we can try to correlate actually the transmission T and the absorbance. We can try to plot them in the same scale. Okay, so what you can see here is that if you have a 10% transmission, okay, this corresponds to 1 absorbance. Why is that? Because as we said, this equals 2 minus, so absorbance equals 2 minus log percentage T times 100. Okay, so the 10% times 100, this will become exactly 10. And then this will become 2 minus 1, and therefore the absorbance will be precisely 1. Okay, the absorbance is precisely 1. And then you can see that starting from there, if we increase the transmission, if more light are transmitted, absorbance actually it will be reduced. Okay, it will be reduced. What about if you have a fully transparent material? Okay, if you have a fully transparent material, transmission equals 100%. In that case, you have a 2 minus 2, so this practically becomes 0 absorbance. Okay, so 0 absorbance means you have 100% of the light transmitted, and if you have a 1 absorbance, it means that you have a 10% light transmitted, and between 0 and 1, you have a between 10% and 100% transmission. Okay, so as you can see here, the definition for absorbance is not exactly the same as the absorption percentage, but they are sort of related basically by the transmission. Okay, by the transmission, it depends on how much you have left after the absorption. So you can correlate them to each other, but at the same time, remember that you do not go automatically from one parameter to the other. You need some other information if you want to find the absorption percentage. Okay, so this is actually the idea here. Okay, this is the idea here. So with that said, that basically concludes our discussion on the optical performance. Okay, we still have I think 15 minutes. So for the remaining part, I would like to start going over some basic physics inside the PN junction, inside the solar cell. Okay, I know that we discussed most of this I think process in the solar PV lecture, but the point is that we didn't actually exactly go into detail, and we didn't actually use a mathematical description to give you the idea about the behavior, right? About some of the phenomena here. So let's do a short revision, right, for the solar PV. Okay. So first of all, is actually in order to understand the solar cell behavior, the PN junction behavior, we have to go back to the fundamentals, which one of them is actually the carrier transport. Okay, the carrier transport. So if we have an electron, if we have a hole, these two are considered charge carriers. How would they move inside the semiconductor? We mentioned that there are 2 possible mechanisms for the carriers actually to move. Okay, so one of the mechanism is actually the drift process, and the other one, if you remember, we just mentioned, is the diffusion process. Okay, diffusion process. What is the reason for drift? What is the reason for diffusion? Drift is coming from electric field. Okay, drift is from electric field. If you apply a certain electric field, right, such as this one here, in this case, actually holes will be propelled to the left side, while electrons will be pushed actually to the right side. Okay, and this is the reason for the charge separation we just mentioned. If you apply the space charge, the PN junction electric field, in this case, you can separate the electrons and holes, and you can push them over long distance. Okay, so this is the drift process. This is based on the drift mechanism. Okay, and then we have the diffusion. Okay, we have the diffusion. What is the reason for diffusion to occur? Do you guys remember?
Concentration gradient.
Very good. Yeah, that is going to be based on the concentration difference. Okay, concentration gradient or concentration difference. If you plot the concentration, on the one-dimensional case, if you have like a peak here, right? This is high concentration, and we have a low concentration here. The tendency is that always a particle will try to go from high concentration to low concentration, and high concentration to low concentration. So it will try to diffuse to both sides of this peak, okay? And that is based on the local concentration gradient. So we have these two mechanisms that will be involved in the PN junction in the solar cell, responsible for the movement of electrons and holes, okay? So for the drift, we just mentioned that this is dependent on the electric field. So the electric field, we're using the letter cosine here. And obviously, if we define a lowercase v as the drift velocity, right, for either the electron or for hole. So this velocity, obviously, it should be proportional to the electric field, okay, to the electric field. The larger the electric field, the larger the velocity we will be starting. Okay, so how do we use that? In our calculation, we just need to define a coefficient. Okay, so instead of a proportional relationship, let us define that the velocity equals a certain coefficient times the electric field. Okay, and we call this coefficient that's going to be the mobility. Okay, the carrier mobility. So we may have a hole mobility, we may have electron mobility. So for a certain species, for a certain carrier type, we will have a different mobility inside the material. Okay, so that is actually the mobility definition. So basically, you can see from the current density definition here, we need to distinguish a hole current. This is the hole current, and we have the electron current here. Okay, so as we said, the mobility times the electric field. This is the velocity. So essentially, what do we have here? We have the charge, the elementary charge Q, okay, times N or P. That is going to be the density of electron and hole, okay, or hole, and then times the velocity lowercase v. Okay. So what does this mean? It means that if per unit volume, right? If inside this volume, we have a certain concentration for electron, that is a lowercase n here, okay? Then over a certain period of time, over a unit time, this whole block of charges, they will actually move in a certain direction, okay? By a certain distance, that is going to be the lowercase v here, okay? So they will have a sort of a displacement over time. And now we know that for current or for current density, essentially this is going to be the amount of charges that is moving during a certain period of time. So we typically say that for current density, this should equal dq over dt. Okay, dq over dt. So the question is, we just need to find that how much charge has displaced during the time of dt. Okay, and essentially, actually, the amount of charges that we have, dq specifically, should equal the concentration here, okay, multiplied by the velocity. Because if you have the unit area concentration, if you have the cross-section concentration, multiply by the velocity, this essentially equals actually the number of electrons in this volume. Okay, we're looking at the volume here. Okay, we're looking at the volume here. How many electrons we have inside? Okay, how many electrons we have inside? And they should equal precisely n times velocity. And then this is only the number, but we need the dq, so we have to multiply by q because one electron gives you 1 unit of charge. Okay, so that is going to be our dq. And then, because we are using velocity, so this happens in the unit time. So essentially, this equation gives us the current density within the material. Okay, so we can write actually a hole current, and then we can write an electron current, for the two carriers, for the two species. Okay, is this part clear? Okay. Okay. And then another thing you have to realize is that when we write the lowercase velocity here, this only represents the average drift velocity. What does average mean? Because usually we look at actually the drift process in a single dimension, in a single direction. Okay, but eventually in the real material, the movement of electrons or holes under a certain electric field, they are not going to go in a straight line. Okay, a straight line path typically is not possible, because actually remember that the electron here has to navigate inside the crystal lattice, and the crystal lattice is a very complex structure. During the movement, actually, they have to navigate around the traps. They have to navigate around actually the silicon atoms that we are seeing here. And sometimes they may have a collision with the silicon, and then they will basically be bounced to another direction. Okay, so the real path of the carrier inside the crystal lattice typically is a very zigzag pattern. Okay, they will go actually sort of semi-randomly in a certain direction, and then they will change their direction because of a collision, because of other physical process. But in general, they will tend to go, over time, they will go from one location to the other. But in general, if the electric field is pointing to the left side, in general, they will go over time to the right side. Okay, so basically the velocity here is only actually indicating the average movement velocity for these specific carrier. Okay, and you can probably see that if the crystal lattice is actually contains less obstacles, then obviously you will have the electrons or holes, they will have an easier time navigating the crystal lattice. Okay, meaning that if you have a less defects in your material, then actually they can go actually in a straighter manner without too much obstacles, without too much difficulties. Okay, so that is why the mobility here, this is actually an indication also for the material structure, for the material quality. Okay, which is why you will find that actually in very ordered material, in very pure material with a very little defects, then usually the mobility will be very high. Okay, on average, their velocity will, under the same electric field, it will be higher. But in very disordered material, typically you will find that the mobility tends to be very poor. Okay, it tends to be very poor because you are expecting a lot of resistance if you want to move across actually the material structure. Okay, so this is the idea for the mobility here. Okay, for the mobility here, and why we need to define such parameter, and at the same time this parameter, it is related to the defects and also to the material purity. Okay, so the second process, as we just mentioned, is the diffusion, which is also responsible for carrier transport. Okay, so as we said, the diffusion or the diffusion current depends on the local concentration difference, or the concentration gradient. Okay, the concentration gradient. And the thing is that if you look at the equation here, actually they have a sort of opposite signs, for Hall current and for electron diffusion current. Okay, the reason for this, is that remember that we always have this term. This is the concentration gradient. Okay, concentration gradient. So let's take the electron as an example. So for electron, to the left side of the scale, we know that this gradient here, the dn over dx, this is going to be positive. Okay, this is going to be positive. So if the concentration gradient is positive, but we know that locally speaking, it always goes from high concentration to low concentration. So the movement of the electron is going to be in this way. Okay, it's going to go from high concentration to low concentration. So it's going to go in the negative x direction. Okay, but how do we define the current direction? If electron is going in the negative side, actually the current for electron is going to go in the positive side. Okay, So which is why for the electron current here, for the electron diffusion current, we have a positive sign here because eventually the electron diffusion current density is going to be in the same direction as the concentration gradient. Both of them, they will be positive. Okay. If you look to the other side, okay, if you look to the other side, the electron movement will go actually to the positive side, meaning that your electron current on the other side is going to become negative, because we have a negative current coming this way. Okay. At the same time, the slope here, it is also negative. The n over dx, it is also negative. So in this case, actually, again, this equation is correct. Okay, this equation is correct. If you do the same thing for holes, remember that for holes, the current direction has to be the same as the movement direction. In that case, actually, if you want to present this equation, remember that there has to be a negative sign here. Okay, meaning that the final diffusion current for the holes will be opposite to the direction of the local concentration gradient. Okay. The only missing parameter we didn't talk about here, the constant we didn't talk about here is the uppercase D here. That is going to be the diffusion constant. So very simply, we are saying that the current density will be proportional to dp over dx or dn over dx. So it's going to be proportional to the local concentration gradient, and the coefficient is precisely the diffusion constant. Okay, it's going to be the diffusion constant. So again, for different material, we're going to have a diffusion constant for electron and another diffusion constant for the holes. Okay, so this is actually the discussion with the diffusion phenomenon. So over time, as we diffuse more and more carriers, of course, the concentration gradient is going to decrease. Okay, so we have a smaller slope here, and therefore it's going to give us less diffusion current over time, typically, if we do not consider the drift process. Okay, so that is actually the other phenomenon we can expect in semiconductor. Okay, so let us talk about this equation, and then we can wrap up today's lecture. So to understand actually the semiconductor or the p-n junction in general, one of the important equations we have to use is coming from the Gauss law, but it is in the one-dimensional form, the one-dimensional differential form. Okay, basically this equation says that if you have that actually the reason for the divergence of the electric field, okay, it is essentially coming from the charge density distribution. Okay, so inside actually a certain space, if you have actually a certain charge density, we use the letter rho here, okay, that denotes a charge density. So remember that we can either talk about electron or hole concentration. Okay, so if you have a certain amount of charges here, this actually will give you a reason for the electric field actually to appear. Okay, because later in p-n junction, we mentioned space charge region, and we mentioned that in the space charge region we will be having electric field. Okay, and this is sort of correlates to the origin of the problem, that if you have a certain charge distribution in the space, you are going to observe actually divergence from the electric field. Okay, and if we talk about one-dimensional case, the good thing is that this divergence automatically becomes the gradient or the slope. Okay, so basically the slope of the electric field in the one-dimensional case, it equals directly the charge density over the constant permittivity, which is the material constant. Okay, which is the material constant. So this actually gives us something like this. Okay, this will give us something like this. Remember, in the p-n junction, inside the space charge region. Okay, so this is the interface between the p time and the n time. Okay, so this is actually the n time. This is the p time. Okay, remember we said that we're going to expect some space charge near the interface. So on one side we have a positive space charge. On the other side we have a negative space charge. Okay, And if we assume a constant space charge here, meaning that the rho here is a constant, okay, rho here is a constant. So if you have a constant rho, then this rho over permittivity will equal basically the electric field gradient, okay, electric field gradient. So your electric field will have the same slope in this region, okay. How can we know that? If we use this equation, you can see that this is the plot for the electric field. So in this region, we have the electric field has the same slope, okay, it has the same slope here. And on the other side, because it's actually becoming negative charges, negative rho. So you have a negative, actually a negative slope here. Okay, a negative slope. And this slope is always constant. Okay, this slope is always constant. On this side, you have a positive slope. Okay, so this is actually the how we can use this equation directly, to understand the PN junction. We mentioned this in solar PV, but the thing is that I believe that we didn't give exactly the mathematical calculation or the mathematical equation here. But this is how you can correlate actually the space charge directly to the amount of electric field that we are getting. Okay, so we will be talking about the rest in the next in the lecture in the next week. Okay, do we have any questions today before we wrap up? Everything is okay, guys? All right. So if there are no more questions, I guess we can wrap up today. Thank you for attending, guys. I'll try to make the recordings available. And how do you find the experience today? So everything is smooth with the Microsoft Teams?
Yes, much better than Blackboard.
Excellent, excellent. And the audio quality is fine, right?
Yes.
Okay, excellent. So if that's the case for next week, at least on Tuesday, we will continue on Microsoft Teams. Okay, so that's it for today. Thank you very much, ladies and gentlemen, and I hope that you have a very nice weekend. Thank you.